welcome to this 13th lecture on electrical machines 2, and last time we were discussing about common underlying principle of operations of rotating electrical machines, and there I told you that for the production of steady electromagnetic torque, one of the conditions all the machines, standard machines must satisfy is that the relative speed between the stator field and rotor field, that must be time invariant. That is, if the stator field is this one and rotor field is this one, I have just drawn with this symbolic line, then the relative speed with respect to a stationary observer, or for that matter any observer, he should conclude that this angle remains same with time. Then only this machine can produce a steady constant electromagnetic torque, which is required if the motor operates at steady state conditions applying a constant opposing torque. That was the first thing. Second thing is, the second condition is the number of poles. I wrote it here, that is the relative speed, and the second condition was the number of poles produced by stator coil currents and number of poles produced by rotor coil currents, those numbers must match. The number of poles will be always even, and also I showed you last time that 2 poles we know how to produce. In this diagram I showed that how can you produce a 4 pole by say a rotor here. It is a rotor coil and it produces 1/4 of this space is north pole, next quarter is south pole, another quarter north pole, another quarter south pole. But to produce that you need now 2 coils. The coil is 1 dashed is a coil, another separate coil is 2 dashed. So, the terminals 1 dashed is available to me, 2 dashed is available to me, and then I will connect them in series like this, and then if you pass some current to test that how many number of poles the machine is going to produce, you excite those coils by direct current, constant current, to examine how many poles are produced. Okay, if it is time varying current, same thing, at any given point of time it will produce 4 poles. Okay. Therefore, you excite it by a constant DC current and it will be producing this one. This I will not do, but I will, if you are following me, then tell me, suppose these are the 2 coils, 1 dashed, another coil is 2 dashed. Remember, 1 is the start, 1 dashed is the finish of the first coil, 2 is the start, 2 dashed is the finish of the second coil. I will ask you to do this exercise, that suppose these 2 coils are once again connected in series, but this way and excited by a battery. Then what you have to do? You have to first show the current distribution, spatial current distribution, and draw the lines of forces and conclude how many poles the same 2 coils, but excited in this way, that is current now flows like this, through the 1 current enters, for the second coil through the 2 dashed current enters, and it is like this. then how many poles do you think this machine produce? This you please do. Then I will be very happy if you can do that. You will be following me then correctly. So, this is the number of poles. Similarly, if you want to create, it looks like, suppose I want to create 6 poles, then each coil produces 2 poles. That way, if you think, it will be 3 coils you will be now requiring. Okay. And can you just suggest that 3 coils will be needed, and show the disposition of the coils separate with terminals of these 3 coils 1 1 dash, 2 2 dash, 3 3 dash, and connect them in series and show that it indeed produces 6 poles. Okay. So, that you try to do. Now, coming to the next rule, that is the next condition, is that the number of poles of the stator and number of poles of the rotors are same, has to be same, in order a steady electromagnetic torque will be produced. Now, how to establish that? We are not going to show it mathematically, but intuitively we can easily understand that it has to be like that. That is, the number of poles produced by stator and number of poles produced by rotor, they must be same. For example, if suppose you have a stator like this, which has produced 2 poles Ns and Ss, and for this you need a single coil. Okay. But a rotor has produced suppose 4 poles. This is the rotor, 1/4 is suppose Sr, then this is also Sr, this is also Nr, and this is also Nr. Suppose a rotor, because the number of poles, how many number of poles will be produced is decided by me. I have made the winding in such a way, I will dictate that terms. Okay. This winding produces 2 poles, this winding produces 4 poles. So, rotor slots I have placed the winding such that it produces 4 poles. Now, the question is, what will be the amount of torque produced? Suppose it is in this position, you can easily see rotor is free to rotate. So, Ns and Sr, it will be having an attractive force. So, torque will be in this direction. But this Ss and this Sr will give you a force like this, and this Nr and this Ns will give you force like that, and this Nr and this Ss will give you force like this. So, eventually the net torque will be 0, is not in this position. So, you can draw in any position, you can show the average, I mean the rotor will not start accelerating at all, because the forces will cancel each other. So, net torque will be, you require 2 equal forces in opposite directions separated by some distance in order to create a torque, and such a situation is not happening here. Therefore, no torque will be produced. So, it is very easy to establish that number of poles which will be produced by stator and the number of poles which will be produced by rotor, they must be same, and that number we know must be an even number. Therefore, these are the 2 basic conditions, and these things must be happening in all the motors. For example, although I in the syllabus I have told that DC machines will not be there, because you have studied there. Let us take the case of DC motor, at least you have read it. For example, we draw the DC motor like this. These are the stator poles, we draw it like this NS, SS, and which is created by field windings which are wrapped around it. So, lines of forces will come out like this way, and they will terminate after going through the iron of the rotor. And DC machine, how do I represent? There are two brushes, these are the armature terminals, you know. Now, suppose I want a motor operation, then what I do is this, I pass some current. Okay. Suppose the current I pass, armature current is in this direction, cross dot. Now, first thing I will, so how many poles this armature coil will produce? It will also produce two poles, cross dot current. There are several conductors here, all are carrying dot current on the left side of the brush and all are carrying cross current on the right hand side of the brush, is not in the DC machines. So, the field will be created also by rotor, that is what I was telling. So, rotor will create field, what will be the direction of the lines of forces? As you can see, it will be like this here. Not there are stator iron like this. So, through that stator iron it will complete its path. I mean it goes like this, it crosses the air gap, then return. This is the direction, red lines are direction of rotor field. Now, in which direction the machine will rotate? It is a motor operation, current I have passed. So, I will apply the left hand rule, here it is dot. So, I will place my finger like this and stator field is going like this, forefinger, this is the current. So, direction of rotation will be like this. So, electromagnetic torque in motor mode operation decides the direction of the rotor rotation. Now, this diagram, this left hand rule I have applied and got this result, but I could also do like this. That is, you look, this is NS, this is SS. Where is NR, SR? If you look at this part of the iron, where from lines of forces coming out, must be your NR, is not rotor north pole, and here it must be your SR, stator north pole. So, you see NS and NR will be repelled and rotor will start rotating. So, left hand rule application of Fleming's is same as now we have extended that idea in terms of magnetic forces, two sets of magnet either repelling or attracting produced by stator and rotor. So, you can see I get the same result, correct, of course, rotor will start rotating. As the rotor rotates, there is another interesting thing. So, if I draw the rotor separately, this side I am just drawing a single conductor, all conductors on this side are carrying dot current and all conductors on this side carrying cross current. In general, you see, if you have not a DC machine, just have two conductors on the rotor, cross dot, just two terminals available, you pass a current, it will produce a field like this, rotor field, fine. Now, if the rotor rotates, then FR2 will rotate, is not, but that is not to be in DC machines. In DC machine, the design is such that with the help of commutator segment and brushes, conductors on the left of this pair of brushes will be always carrying current in a particular direction, always. As time passes, the left hand side will be filled by newer conductors which are crossing over. This conductor after some time will come here, but no matter when it comes here, it has to carry that constant magnitude dot current. Similarly, any conductor here switching over to this side as the rotor rotates will be always carrying cross current. Therefore, you see rotor rotates, but the field created by it remains stationary. No, it is fixed. Therefore, a stationary observer in a DC machine, I am trying to check whether those conditions are satisfied. Of course, number of poles are same that I have seen, and with respect to it, what is the field of the stator? Stator field is stationary, and also, so stator field is like this. He will observe that stator field is stationary. So, also he will observe that the rotor field is at right angles and it remains stationary no matter at what speed the machine is running. So, the most interesting thing is this type of thinking is the most fundamental. A single coil without any commutator segment brush, you excite it with current, in space a field will be created and this field will remain stationary so long this structure is stationary. Now, suppose I give a push to it, this fellow starts rotating this way, then your FR2 will go on rotating. So, that is why whoever suggested this way of constructing a machine like a DC machine, it is a marvel. I mean that commutator segment and brush always make sure that the currents on one side is always cross and current on other side is always dot, and therefore, the field produced by rotor, although rotor is rotating, is fixed in space. It never goes this way that way as it will do like this. So, that thing is taken care of commutator segment and brushes. So, here we see that conductors are rotating, but field is stationary, and it must be stationary because DC motor we know it produces a steady electromagnetic torque. What about the other thing is possible, that is coil will remain stationary, but the field created by the coil currents will appear to move. Yes, that is also possible. That is what Nikola Tesla suggested. For that, of course, you require not a DC supply, some AC supply and distributed coils, those things will come. But the important point is when I say the field is rotating, you should not be bothered about the fact whether this stator is stator, whether that rotor is stationary or not. Anyway, either way it can do. Rotor may remain stationary, rotor it carries 3 phase balanced current, it is observed that it produces a rotating field. Anyway, so that is the thing, but here two things I told. One is that instead of applying left hand rule, if you know the direction of rotor currents in a DC machine like this, you can figure out where is NRSR and where is NSSS, and based on this you can decide in which direction it will start moving. That is why I am telling it is that is how we will always think that two sets of magnets are interacting and giving you torque. Okay. Achha, some diagrams has been made, so that I will try to use that, although I was drawing roughly some diagram. For example, you see It is a 4 pole. Here I have not shown the windings, stator windings. Now, we are matured enough to understand what I mean by this NS, SS, NS, SS. Okay. And suppose rotor produces 2 poles N and S with rotor windings, that also I have not shown. Suppose it is in this position now, rotor is in this position. Will rotor experience any torque or not? See, this N and this stator N, it will be repelled in this direction and it will be attracted by S. So, in this direction only you get a force on this side, and here this S will be repelled by this and attracted by this S. So, it will be like this. So, you have two forces, one is this way, another is also this way. Can these two produce a torque? No. You require this force and the force this side should be opposite, then only two parallel forces separated by distance can cause a couple or torque to exist. Therefore, why then it is not experiencing a torque? It is because of the fact someone has thought that any number of poles I produced on stator, any number of poles I produced on the rotor, they will interact and give me torque, but that is not true. The number of poles produced by stator and produced by rotor, they must be same. That is why for example, this case as I was drawing here, suppose 4 poles have been produced by stator coils and 4 poles has been produced by rotor coils. Of course, it is a small angle exists. So, this north pole will experience a force in this direction like this repelled, and this south pole will also repel it, it will experience a force in this direction. This north pole, as you can see, will be repelled like this, and this south pole will be also repelled by this. So, this rotor will have torque because of these two forces and these two forces, and it will start moving in this direction. So, in any position you place them, you will find net torque exists. So, we now know the basic principle of operation or underlying principle of operation is that number of poles produced by stator and rotor must be same, and for steady production of torque, the angle between them must be same. The other point, that is angle between them is same, I discussed at length in my last lecture. So, that is the after we have understood this, I will now talk about the key terms that I will be using, because we have till now not done any mathematics, rather very little mathematics, and intuitively we try to understand what must be going on in any rotating machine. Okay. Now, what I will do? I will try to get the B distribution along the air gap of a machine, of a rotating machine, of course, of a machine. How to get it? The problem is like this, that is suppose this is your stator and here is a coil in this pair of slots, 2 pole configuration. You can immediately understand whether I have drawn for 2 poles or for single pole. This is cross current, this is dot current I am passing. This is a 1, this is a 1 dashed, and the lines of forces. Rotor I am not drawing, it is there, rotor iron, through which the flux path will be completed and it will be like this. And there are several others. Not a very good diagram, but it gives you the idea of what I meant to say. So, what will happen? This hub will become a south pole, this hub of the iron will become a south pole, and this hub will become a north pole, NS and SS stator. Now, the question is, I want to now estimate that what will be the strength of that field and what will be the nature of that field. I want to do it. So, for that, and mind you, there is rotor iron here, and rotor coils I am not drawing now. I want to show rotor iron. I want to find out the field distribution, and this is the air gap. So, what I will do first, I will draw the developed diagram of this. So, I will cut it like this and spread it out in this fashion, so that you will get a picture like this. These two slots and this outer thing is here, and here is air gap, and this is rotor iron. This is rotor iron. I think you have got the idea, and here is 1 dashed and here is 1, is not? This is stator iron, and I have assumed the current as cross and this is dot. And just first I will draw the lines of forces. It will be somewhat like this, cross current, and I will draw the lines of forces. It will be like this. Symbolic one I have drawn, there are several. So, this space will become stator south pole from this to this, and this space from which lines of force come out of this iron is your NSS and NS. Okay. Now, I want to understand what will be the strength of this B and how it will look like. Will its value remain same? Will it be sinusoidal? Such things I will now discuss now. So, thank you, and try to understand this disposition of the coil. Okay.